Okay, so we've got one more Feynman diagram to write down. So let's go ahead and do that. So what is this Feynman diagram? So it'll be plus. We've got two vertices. So we'll have a minus 4 factorial I G Z squared. Then what's the combinatoric factor? Well, there's no closed lines. There's no equivalent diagrams. There's no equivalent vertices, but there are two equivalent lines. And again, the two lines in the loop are equivalent because they both start on the top vertex and end on the bottom vertex. So we need a factor of 2 for equivalent lines. Then we need to integrate over the loop momentum. This will be an integral d4L over 2 pi to the 4. We'll get an I z inverse over L squared minus M squared plus I epsilon, and we'll have an I Z inverse into L plus P1 plus P4 squared minus M squared plus I epsilon. Good. So we've summed all of the Feynman diagrams now. What should the sum be equal to? Well, this should be equal to minus 4 factorial times by I times by the physical coupling, GP. Okay, so this is the equation that we get to match the coupling. Good. Okay, now let me just rescue the two equations from above. So, okay, they're pretty close. Good. Okay, very good. Let's just bring this down. Actually, let's put this here. And let me rewrite this first condition a slightly different way. So let's remove the box. We'll put it over here. Minus 4I G minus 4 factorial minus 4 factorial I times by the physical coupling GP, and this is plus order G squared. So we have now worked to one loop, and we have these three equations. And what would they allow us to do? Well, your experimental colleague will have gone away and measured. He will come and tell you GP is some value, like maybe 1,6 times 10 to the minus 19 coulombs. He will tell you MP squared is some value. So MP is something like 10 to the minus 31 or whatever it is kgs for an electron. Okay. And you shouldn't really use kgs as a unit. So maybe MEVs or something like that. But the point is, this would be some number and that would be some number. And then using these two equations, what are the only things that are unknown? Well, you've already set the value of Z, so Z is no longer an unknown, but M is an unknown and G is an unknown. So those are the only unknowns that you've got, M's and G's, and they appear all over the place in these equations. But you now have two equations for these two unknowns. So you could actually solve for these unknowns, M and G, and you could work out what M and G are in terms of the physical coupling and the physical mass squared, which are actual numbers. Once you've fixed M and G, every other quantity that you calculate will be an actual number, and you can compare it to experiment. So this would be called doing the renormalization of 5-4 theory to one loop. Good. Okay, so there's two comments I'd like to make. So the first comment is regarding this coupling strength renormalization. one of the things that you might have been puzzled about, why didn't I add this diagram? Well, it certainly looks like it's connected. So it is connected. So that's good. And it looks like it's one loop. So why on earth didn't I include this? Well, the reason for that is when I amputate, so after I've amputated, all that I get is that. And that has been included, okay? That's the vertex over there. And really, the way to intuitively understand why we don't need to include this is because this, what's going on here, this loop is dressing a leg. And we know exactly what that dressing of the leg does. That's where the second contribution sitting over here came from. That was from the loop dressing the leg. So this is not an effect related to the coupling. It's an effect related to propagation until you get to the vertex. So that's why we don't include a diagram like that. So anything that is just affecting how the external legs are affecting the values of the external legs are not included when we amputate the external legs, okay? Now, the next comment I wanted to make is you may be feeling a little bit unsatisfied with these three matching conditions. You see, to actually use these equations looks pretty difficult. How on earth are you going to solve for M and G from these three equations? They're not very explicit because they've got all of these integrals appearing everywhere. Well, there are tricks that are known to perform Feynman diagrams, and I'm going to teach you those tricks. Once you know those tricks, basically evaluating Feynman diagrams becomes a procedure, an algorithm. You simply apply the algorithm and then you'll get some answer. Now, for simple diagrams, you rarely get a number. You get some numerical value. But for more complicated Feynman diagrams, you're typically left with some integrals over what are called Feynman parameters. And those do need to be performed numerically, but they can be performed numerically. So we are going to learn the tricks to actually evaluate these Feynman diagrams to get explicit expressions that you can then go ahead and use. All of the integrals of momenta will be gone. And in the next chapter, we're going to be learning how to do the Feynman diagram integrals. Great. So this is our discussion of phi-4 theory to one loop. Now let's just discuss the exercises for this chapter.